This video is about plating and reading protein samples. The required materials are protein standards. You can see video 1 for how they're made. Bradford reagent, 96 well microtiter plates, a plate reader, multi-channel pipettes and the correct pipette tips, as well as the all-important marker pen. Each well on the 96 well microtiter plate is individually identifiable by an array of alphanumerical and numbered code. You've got numbers on the top edge here and letters on the left edge, and if you combine G1, G5, A1 for instance, you can identify each well. So here on the lid I'm writing the concentration. So 0 is for R blank, 0.2 is for 0.2 milligrams per mil, then there's 0.4, and we speed it up a bit all the way to 1 milligram per mil. And you can see, and our template for how we're going to plate the protein samples. We set the pipette to 10 microliters and then pipette 10 microliters of each concentration into the bottom of the well. You go right to the bottom and you can see the liquid building up as it exits the pipette. Then we change the tip and do the same for each of the other concentrations. I'm speeding this up because it does take a while. So we have to change the tip for each of the concentrations so that we don't get contamination or cross-contamination between the different concentrations. I'm now going to take 290 microliters in the multi-channel pipette and add it to the wells. You can see it's all brown in the blank, and the further right we get, it gets bluer and bluer. And this is because the Bradford reagent, if you remember, is reacting with the protein, and as it does so, the Bradford reagent turns, or the protein Bradford complex turns blue. And the more protein there is, the more intense the blue color becomes. And you can see there's a nice concentration gradient, and there's a reasonable reproducibility as well. We wait 10 minutes or so and then take it to a plate reader. In this case it's a Spectromax, which is set to a spectrophotometer setting. We need to adjust the settings in such a way that we have the right wavelength. And we can do that by saying we want a one-off measurement at 595, which is the absorption maximum for the protein Bradford complex for the blue color. We also want to shake it a bit so that there's no bubbles. And I've turned the background noise on now so that you can hear what the machine sounds like, because as it shakes you'll hear quite a racket. So we press go. So that's it shaken. And then these other little noises as the plate moves through the light beam, and each well is illuminated, and the absorption of the light going through the different concentrations is measured. The data is then displayed on the monitor, and it's exactly in the same pattern as the 96 well plate. That can then be transferred to an Excel sheet, and then we have to format the data. So I'm highlighting our data. All the other wells are empty, and that's on the right is the wavelength 595. So we've got the correct wavelength. So now I'm going to play around with the data in such a way that we can actually create a calibration curve, because that's essentially what we want to do here. So I'm getting rid of all the unnecessary stuff. so it's nice and tidy. The first thing I'm going to do is label everything. It makes sense now, but it might not in a few months' time, for instance. So 0, 0.2, 0.4, 0.6, 0.8, and 1 milligram per mil. It's important to have the units as well. And then we're going to calculate the average. We'll just make a nice line under there so it looks tidy. Then we're going to highlight the concentrations and the readings. And we're going to insert a scatter plot. And what you can see nicely here is that on the y-axis we have the reading, which is the dependent variable of our graph, and on the x-axis we have the protein concentration, which is the dependent variable, the independent variable. So just tidy it up a bit, give it proper labeling. And you can see I made a typo at the top in the table. It says milligrams per liter. It should be milligrams per milliliter, but I'm doing it correctly on the graph. So I see I haven't done it correctly. It's still milligrams per liter even on the graph, so that's obviously not correct. It's milligrams per milliliter. So Excel has now drawn the trend lines through the data points for me and produced a linear equation. And what I can see here is that the intercept between the y-axis and the trend line is the background. That has to be subtracted from all the other readings, and you can see the equation does that for me. It also gives me the R-square, the correlation coefficient of 0.99, which means we've done a pretty good job.